Welcome to Lab 5 Magnetic Braking with Faraday, our last lab. Introduction. The objective of this lab was we were to obtain data from dropping a bar magnet into a roll of aluminum foil. The results of this lab was that the experimental time was 1.29 seconds, but the computational time was 1.87 seconds. Concepts. So there are some important concepts to understand going into this lab, such as Faraday's law, the Biot-Savart law, Ohm's law, Newton's second law, and then the magnetic flux of a dipole. So the assumptions in the models. So we are assuming air resistance is negligible and the only forces acting upon the magnet are gravity and the magnetic force from the aluminum tube. The system would be the magnet and the aluminum tube, and the surroundings would be everything else. So you're going to start off by finding the north pole of the magnet using a phone, so the magnetometer on the phone, like we did with Lab 3. Then you're going to drop it in the tube multiple times, recording how much time it takes each trial, and then find the average. So the magnet itself is going to be modeling a magnetic dipole, which in the bottom left corner, I drew to represent it. So data. We measured the time by taking videos of each time we dropped the magnet. So we took measurements of the materials beforehand, of course, so the length of the tube and then the radius of the inner part of it. And the mu mag comes from lab 3. So you have, that should say trial one, I think our trial one got it was 1.5, and then trials 2, 3, 4, and 5, and then at the end you just take the average, which was for us 1.29 seconds. So this is our glow script code. You have to start off with your physical constants, and then you can put in the formulas you already know, but here it's we have to match the experiment, so like the length and the width and then the inner radius. This is where you start to put in the formulas that you know for the magnetic field of the bar magnet. So that's just the Biot-Savart, and then R mag and R hat to define those terms. And then here it's the magnetic flux. So we have to put in those formulas because all of these are taking part in the overall experiment. So then we have here the gravitational force and then the current in the ring. So input those. And then lastly, you have the B field at each ring and then the net force on the magnet. And then here, once that's all, and you type that in, you have your model. And so as you can see here, it took approximately 1.87 seconds computationally for the magnet to fall through. And I took a little snapshot of what it looked like because by the time it's all done, at the very bottom of the tube, it's just going to be blue. So the change in magnetic flux, it increases in the negative y direction, which is the way the magnet is falling. The blue part resists this, so it's making the magnetic force upward. Blue is the current in the counterclockwise direction, and red is the current in the clockwise direction. Errors. So human error is always a possibility. We may have measured time incorrectly. Also, if our mu from lab 3 was wrong, that would alter the computational model. I did mess around with mu, and the higher it gets, the slower the bar magnet fell. The point where I think at one point I put it in as like 5 point something, and it took over 60 seconds for it to fall. But as you can see here, the computational time is longer than the experimental time because 1.87 seconds is a lot, or not a lot, but it is significantly longer than 1.29 seconds. And I'm getting that from here, the tube, the time in tube. All right, discussion and conclusion. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So essentially, if this were to happen, the induced current in the tube would be greater. Basically, it creates a larger force on the magnet, which sort of, it goes against gravity entirely, counteracts it, which means that the magnet would not fall, so it would just stay in place. So the second what if is that what if there were holes or slots that were cut into the tube? How would this affect the ring currents in your model? Okay, so if there were holes and slots cut into the tube, the induced current would decrease due to the holes, so the magnet would be falling much faster. The magnet force or the magnetic force upwards would be a lot less in this scenario. Thank you so much for watching.